Today, we are not just talking about biology. We're talking about logistics.
The ultimate supply chain, really.
The ultimate, yeah, I want you to just imagine the most complex shipping network on Earth. Maybe it's Amazon Prime during the holidays or FedEx trying to coordinate planes and trains and trucks globally to get a package to your door in, 24 hours?
It's a massive undertaking. Mind-boggling, really.
It is. But now I want you to realize that those networks, as impressive as they are absolute child's play compared to what is happening inside your own chest right this second.
It's not even close, is it? When people think of respiration, they usually just think of the mechanical part, the lungs expanding and contracting.
Right, in, out, simple.
But that's just the loading dock.
Uh-huh.
That's the warehouse door opening. The real story, and what we're digging into today, is what happens after the delivery arrives. We're looking at Chapter 41, Transport of Oxygen and Carbon Dioxide in Blood and Tissue Fluids.
So we are tracking the specific journey of a single gas molecule. We're going from the lungs onto the highway of the bloodstream, offloading at the cell, and this is the part I think is actually the most complex, picking up the trash.
Picking up the exhaust, yeah. The carbon dioxide to bring it back.
And looking at these sources, I have to say the mission of this deep dive is to explain the physics and the chemistry that make this all possible. Because, I'm looking at the graphs, there are a lot of curves, a lot of partial pressures. It looks intimidating.
It can be. I mean, you see terms like dissociation curves, sigmoid shapes, pressure gradients. It honestly looks like an engineering manual for a machine you didn't know you owned.
Yeah, exactly.
But our goal is to translate that medical speak, into concepts that actually make sense. Because when you strip away the jargon, what you find is this incredibly elegant system of what the source calls safety margins. The body is over-engineered.
Over-engineered. I love that phrase. It implies redundancy. It implies a backup plan.
In the best possible way, yes. Multiple backup plans, layers upon layers of safety nets.
So, okay, give us the lay of the land. What are we actually working with here? What are the key players in this story?
Well, we have a few key players. First, you just got the simple physics of diffusion. That's the foundation. Gas is moving based on pressure.
High to low.
High to low, always. Then we have the hero of the story, which is hemoglobin. It's not just a carrier. The source describes it as a buffer.
A buffer. Okay, when I hear buffer, I think of, chemistry class and pH balance, or more likely a YouTube video that won't load.
Right. Well, in this context, think of it as a stabilizer. It actually stabilizes the entire oxygen environment for your tissues, which is a fascinating concept we'll definitely get to.
Okay.
Then you have the really clever chemical interactions, the Bohr effect and the Haldane effect, which is basically how oxygen and carbon dioxide talk to each other and influence each other's movement.
So they're not just passive passengers.
Not at all. They're actively kicking each other off the bus when the time is right.
Yeah.
And finally, yeah, we have to touch on the dark side, carbon monoxide poisoning and the chemistry of waste removal.
Okay, let's unpack this. But before we get into the nitty-gritty, you found a statistic in the source that it just completely blew my mind. It's about how fast this all happens.
Right. This is the hook for me. This is the how on earth moment. If you look at the blood flowing through the capillaries in your lungs, it is moving fast. The source points out that a single red blood cell spends only a fraction of a second in the pulmonary capillaries.
How small of a fraction are we talking about here? Like a couple of seconds?
Less. About 3/4 of a second.
Yeah.
0.75 seconds.
That's less than a single heartbeat.
It is. In that tiny, tiny blink of time, that red blood cell has to enter the capillary, align itself, negotiate all this complex chemistry, grab a full load of oxygen, dump its entire load of carbon dioxide, and then get out.
It's like trying to fill up your car's gas tank while driving past the pump at 60 miles an hour.
That's the perfect analogy.
Yeah.
And not just getting a splash of gas in the tank.
No, filling it to the brim.
Filling it to the brim. The blood leaves almost perfectly saturated, 97% saturation.
And the question is, how did nature pull off that engineering feat? That's what we're going to try and answer.
It's a combination of brute force physics and some very, very clever chemistry.
All right, let's start at the beginning. Section 1, the downhill slide. We are in the lungs. We've just taken a breath. What drives oxygen into the blood? Is there like a pump for the gas?
No mechanical pump for the gas itself, no. It's all about the gradient. The fundamental rule here, the engine of respiration, is that gases always move from an area of high pressure to an area of low pressure.
And we call this partial pressure, right? The source uses that term constantly. PO2 of this, PO2 of that.
That's the one, PO2.
How should we visualize that? What is partial pressure? Is it like water pressure in a pipe?
That's a decent starting point.
Yeah.
Think of it like a crowded room. Partial pressure is basically a measure of how many gas molecules you have in a certain space and how much they're banging against the walls.
Okay.
So if you have a high partial pressure, you have a mosh pit. Lots of molecules, tons of energy, all of them pushing outwards trying to get out.
A mosh pit. I like that. High pressure equals a mosh pit. So low pressure is what? An empty lounge?
An empty lounge, exactly. So in the alveoli, those tiny little air sacs deep in your lungs, the oxygen partial pressure is huge. It's about 104 millimeters of mercury, or mmHg. That's our mosh pit.
104, okay.
Now, you look at the venous blood that's coming back from the body. It's done its job. It's dropped off its oxygen, and it's coming back to get refilled. Its PO2 is only 40 mmHg.
Whoa, so 104 in the lungs versus 40 in the blood. That's a massive gap.
It's a difference of 64 mmHg. In the world of gas diffusion, that is a colossal initial pressure difference.
So the oxygen doesn't just, like, drift across.
It absolutely rushes into the pulmonary capillaries. It's not a gentle drift, it's a flood. It's like opening the doors of a packed concert hall into an empty street.
And this brings us to that safety factor you mentioned earlier. There's a graph here, figure 41:1. It's charting the uptake of oxygen as blood moves through that 0.75 second journey in the capillary. Walk us through what this curve looks like.
Okay, so imagine the x-axis, the horizontal line, to the length of the capillary. The blood enters on the left and exits on the right.
Got it.
The axis, the vertical line, is the oxygen pressure in the blood. So you start at the bottom left at 40 mmHg. That's the deoxygenated blood coming in.
And then what happens?
The curve shoots up almost vertically. It's a ridiculously steep climb, like a rocket launch.
Because it fills up fast.
Incredibly fast.
Yeah.
The blood PO2 rises to match the alveolar air. It hits that 104 mmHg level within the first third of its transit through the capillary.
Wait, only the first third? So you're telling me for the remaining 2/3 of its journey through the lung capillary, the blood is just cruising. It's already full.
Essentially, yes. The deal is done. It's already fully saturated. It's just enjoying the ride for the last 2/3 of the trip.
That seems inefficient. Why would you build a highway that's 3 times longer than you need to get to the destination?
But this is the critical safety factor. This is the over-engineering. Think about when you exercise.
Yeah.
Your heart starts pounding, right?
Right. Blood flow goes way up.
Exactly. The blood pumps much, much faster, which means the time each red blood cell gets to spend in the lungs gets cut way down.
Okay. So that 0.75 seconds might become, 0.4 seconds?
Less than half, even. During strenuous exercise, your cardiac output can skyrocket, and the time blood spends in the pulmonary capillary can be reduced to less than half the normal time. So if the blood required the full length of the capillary to get oxygenated at rest,
You'd be in big trouble during a sprint. You'd leave the lungs with your tank half empty.
you'd pass out on the treadmill. Your muscles would scream for oxygen that just wasn't there.
But because it normally saturates in that first third?
Even if you cut the transit time in half, or even a little more, you are still using enough of the capillary to become fully oxygenated.
It's a built-in redundancy, a buffer zone.
It's the ultimate safety net. The source notes that during exercise, the body requires as much as 20 times the normal amount of oxygen. Now, other things help. You get improved ventilation, increased surface area from more open capillaries, but this rapid saturation curve is the real guarantee. It ensures that unless your lungs are severely damaged, your blood will leave fully loaded no matter how hard you push it.
That is brilliant. It's like having a runway that's 3 times longer than your little Cessna needs, just in case one day you need to land a giant military transport jet in an emergency.
Precisely. You build for the worst-case scenario.
Okay, so we've loaded the truck. The blood is leaving the lungs at a pressure of 104 mmHg. It's fully topped off. Now we head out to the body. But I'm looking at the next section of our notes here about something called shunts and low. It looks like we lose a little bit of that precious cargo almost immediately.
We do. And this is a nuance that's often missed in basic biology classes. You would assume the blood leaving the heart and going into the aorta is at that perfect 104 mmHg.
I would, yeah.
But the source corrects this. By the time the blood actually enters the aorta to go out to the body, the pressure has already dropped to about 95 mmHg.
Where did we lose that 9 mmHg? Did it just leak out?
In a way, it's called venous admixture, or more simply, shunt flow.
Shunt flow, okay.
So think about it this way. About 98% of the blood that enters the left atrium of your heart just came from those alveolar capillaries. That stuff is oxygen-rich, prime vintage. 104 millimole Hg.
The good stuff.
But there's another 2% of blood that gets mixed in. This blood comes from the bronchial circulation. This is the blood that was actually feeding the deep tissues of the lungs themselves.
Ah, so the lungs need to eat too. They aren't just a pass-through station. The walls of the warehouse need power.
Exactly. The lung tissue needs oxygen to survive, just like your bicep does. And that blood, after it feeds the lung tissue, is used. It didn't pass the gas exchange areas, it's shunt blood. It bypassed the main oxygen loading dock.
So what's its oxygen pressure?
It's low. It has a PO2 of about 40 millimole Hg. It's dirty, deoxygenated blood.
Where does this dirty blood go?
It dumps right into the pulmonary vein, mixing with the clean stream just before it gets to the heart.
You're kidding me. So you have this huge, pristine bucket of 104 millimole Hg blood, and right at the end, someone pours in a little cup of 40 millimole Hg blood and stirs it all up.
And the math of that mixture results in a final average pressure of about 95 millimole Hg. And that is what actually gets pumped out to your toes and your brain.
That feels like a design flaw. I mean, why not route that dirty blood back to the start, back to the right side of the heart to get reoxygenated properly?
It's a great question. It's likely just an anatomical trade-off. Piping it all the way back to the right atrium might require more complex plumbing than just dumping it into the nearest big vein. The body seems to have accepted a tiny 2% efficiency loss in exchange for a simpler architecture.
Good enough for government work, I guess. Okay, 95 is still pretty good.
Yeah.
So now we're traveling through the arteries. We arrive at the tissues. We're in the capillaries surrounding, let's say, a muscle cell. What's the situation there?
Now, the whole gradient reverses. The blood is arriving hot at 95 millimeter Hg. But the interstitial fluid, that's the soup that all your cells are sitting in, is at a much lower pressure.
And what's that pressure?
It's about 40 millimeter Hg.
Ah, so the slide goes the other way. High pressure in the blood, low pressure in the tissue fluid. Mosh pit in the capillary, empty lounge outside.
Precisely. And so you get this huge pressure release, a 55 millimeters G gradient. Oxygen diffuses rapidly out of the capillaries and floods into that interstitial fluid.
And what's left in the blood when it leaves?
By the time the blood gets to the end of the tissue capillaries to head back to the heart, its pressure has dropped all the way down to 40 millimole G. It effectively equilibrates with the tissue fluid.
There's a really interesting graph here, figure 41-4, that talks about the mechanics of blood flow versus metabolism. It seems to imply there's a limit to how much oxygen you can force into the tissues just by, pumping blood harder and faster.
Yes. This is what the source calls the limit of infinite blood flow. It sounds like a concept from a sci-fi movie, but it's just chemistry.
The limit of infinite blood flow. Okay, break that down.
So imagine you could increase blood flow to a tissue by 400% or 1,000%. You're just rushing fresh, oxygen-rich blood past the cells constantly. You would think the tissue oxygen level would just skyrocket, right?
Right. More flow equals more oxygen. That seems logical.
But look at the curve on the graph. As blood flow increases, the tissue oxygen level goes up, but then it flattens out. It hits a ceiling. And that ceiling is the arterial pressure.
95 million or Hg.
95. You can't deliver a pressure higher than what you're carrying in the first place. So no matter how fast your heart beats, you can't make the tissue oxygen pressure go above 95. You hit a hard chemical limit.
You can't give what you don't have. Makes sense. But what about the other side of the equation? What if the cells start using the oxygen faster?
That's the metabolic rate. Another line on the graph, if your cells increase their metabolism like during exercise, they're consuming oxygen much more rapidly. This will lower the interstitial fluid PO2.
Yeah.
So unless you increase blood flow to compensate, the oxygen levels available to the tissue will drop.
So it's a constant tug of war. Delivery speed versus consumption speed.
A dynamic equilibrium, always adjusting.
Let's talk about the final destination then. The cell itself. We've gone from lungs to blood to the interstitial fluid. Now we need to get inside the cell membrane.
Right, the intracellular PO2. This is what the mitochondria actually see. The source says this ranges from as low as 5 mmHg to as high as 40 mmHg, but on average, it's about 23 mmHg.
23? That seems pretty low compared to the 95 we started with in the arteries.
It is, but here is the most crucial insight, maybe in the whole chapter. The chemical process is inside the cell. The mitochondria burning fuel to make ATP. They only need a tiny, tiny amount of oxygen pressure to run at full speed.
How tiny are we talking?
1 to 3 millimeters of mercury.
Get out of here. Really, the entire cellular engine works perfectly fine on 1 to 3 millimilli Hg, and we typically have 23 just sitting there.
Exactly. That is another massive margin of safety.
So what's the limiting factor then? If I'm running and I feel like I'm running out of energy, it's not because I'm running out of oxygen in my cells.
Almost never. The source is clear on this. The rate-limiting factor for your energy production is almost never oxygen availability. It's actually the amount of ADP adenosine diphosphate available to be recharged into ATP. As long as the oxygen pressure is above that critical 1 mHg threshold, the machinery runs at maximum capacity. The amount of fuel you're trying to burn is the bottleneck, not the oxygen.
That is deeply comforting, actually. So even if I'm, holding my breath for a bit or running up a long flight of stairs and my tissue oxygen drops a bit, my cells aren't necessarily starving yet. They've got that huge buffer zone between 23 and 1.
Correct. The system is designed to handle wild fluctuations without crashing the machinery. You could, in theory, lose 90% of your intracellular oxygen pressure and still produce energy at the exact same rate.
Wow, okay. Speaking of buffers, let's move to section 3, the smart transporter. We can't talk about oxygen without talking about hemoglobin.
Absolutely not. I mean, if we had to rely just on oxygen dissolving in the water of our blood plasma, we'd be dead in minutes. It simply isn't soluble enough to support our metabolism.
So how much of the work is hemoglobin doing?
Almost all of it. 97% of the oxygen in your blood is carried chemically bound to hemoglobin inside your red blood cells. Only a tiny 3% is just dissolved in the plasma.
So hemoglobin isn't just the truck fleet, it's the whole logistics industry.
It's the fleet, it's a logistics manager, and it's a smart warehouse all rolled into one.
And the source spends a lot of time on this thing called the oxygen-hemoglobin dissociation curve. It's figure 41-8. It's shaped like a stretched out S. Why is that S shape so important? Why isn't it just a straight line?
That S shape, or the sigmoid curve, is the secret to hemoglobin's intelligence. It's a concept in biochemistry called cooperativity.
Cooperativity, like the molecules are all working together.
In a way, yes. Imagine a hemoglobin molecule has 4 seats for oxygen molecules. When the first oxygen molecule comes along and tries to sit down, it's actually kind of hard. The seat is stiff.
Yeah.
But once that first one manages to bind, it causes the entire hemoglobin molecule to change its shape.
It loosens up.
It loosens up, it opens up, it becomes stickier. It actively invites the second and third oxygen molecules to sit down much, much more easily.
So it's like molecular peer pressure. Come on in, the water's fine.
That's a perfect way to describe it. And that cooperative binding is what creates the steep upward slope in the middle of that S-curve. A small change in oxygen pressure leads to a huge change in how much oxygen gets loaded on.
Okay, that explains the loading. Let's look at the numbers on the curve.
Okay, so look at the very top of the curve, the flat part. In arterial blood, where the PO2 is about 95 millimilli Hg, hemoglobin is roughly 97% saturated. It's holding onto its cargo very tightly. It's full.
Makes sense. That's in the arteries on the way to the tissues.
Right. But now look at what happens when it gets to the venous end after it's passed through the tissues, where the pressure has dropped to 40 millimilli Hg. You look at the curve, and hemoglobin is still about 75% saturated.
Wait, 75%? That means it only dropped off 25% of its load. That seems incredibly inefficient. We drove the truck all the way out to the tissue and only unloaded a quarter of the boxes.
It seems that way at first glance, doesn't it? That percentage is what physiologists call the utilization coefficient. And at rest, yes, we are extremely conservative. We only use a quarter of the oxygen we carry.
But why? Why carry all that extra weight, all that extra oxygen, if we aren't even using it?
Because that's your reserve tank.
Yeah.
That 75% is what you tap into when things get serious. During heavy exercise, that utilization coefficient shoots up from 25% to 75% or even 85%.
Ah, I see.
Because we have that huge reserve already on the truck, the body can suddenly extract nearly everything it's carrying if it needs to. You can triple your oxygen delivery to a muscle without even increasing blood flow, just by extracting more of what's already there.
Okay, that makes sense. It's the body's emergency supply. But there is a deeper function here, isn't there? The source calls hemoglobin a tissue oxygen buffer.
Yes, and this is one of the most important and maybe least intuitive concepts in respiratory physiology.
So buffer usually means something that dampens change. How does hemoglobin dampen changes in oxygen?
It stabilizes the oxygen pressure in the tissues. Let's use an extreme example from the source. Let's say you go mountain climbing, or an airplane cabin suddenly depressurizes. Your alveolar PO2, the pressure in your lungs, might fall from a normal 104 all the way down to 60 millimille Hg.
That sounds dangerous. That's a huge drop of over 40%.
It's a massive drop in the environment. You'd think the oxygen delivery to your tissues would crash. But look at the top of that S-curve again. It's very flat up there.
Right.
Because it's so flat, even at a lung pressure of 60 millimille Hg, hemoglobin is still 89% saturated. It barely dropped from 97%.
Wow. So even though the air pressure in my lungs crashed by 40%, the delivery truck leaving the lungs is still 89% full.
Exactly. And because the tissues at rest still extract roughly the same absolute amount of oxygen, about 5 milliliters per 100 milliliters of blood, the venous blood just comes back a little emptier. Maybe its pressure drops to 35 millivittel Hg instead of 40. The net result is that the tissue oxygen pressure hardly changes at all, despite these wild swings in the outside environment.
Hemoglobin absorbs the shock?
It's basically a voltage regulator for oxygen. It keeps the output to the tissues incredibly steady, regardless of massive fluctuations in the input from the lungs. It guarantees your cells see a consistent, stable oxygen environment, whether you are at sea level or at 10,000 feet.
That is an incredible piece of chemical engineering. But it's not just a shock absorber, it's also adaptable. This brings us to section 4, the shifters. And the Bohr effect. I love this name. It sounds like a spy novel or something. The Bohr effect.
It's all about tactical chemistry. The bond between oxygen and hemoglobin isn't static. It's not a fixed strength. It actually changes its strength based on the chemical environment around it.
So the truck can decide how tightly to lock its doors depending on the neighborhood it's in.
That is a perfect analogy. And the key is what we call a right shift in that S-curve. When the curve shifts to the right, it means that for any given oxygen pressure, hemoglobin is less saturated. It has a lower affinity for oxygen.
It lets go of oxygen more easily.
It becomes less sticky.
So what triggers this right shift? What tells the hemoglobin to open the doors and start unloading?
Well, think about a muscle that is working really, really hard. What is the chemical environment inside a sprinting leg muscle?
Okay, well, it's burning a lot of fuel, so it's producing a lot of waste. So tons of CO2.
Yeah.
Exactly.
Yeah.
Carbon dioxide. What else?
All that CO2 mixing with water, it's probably getting acidic. Lactic acid, too.
High acidity, which means a lot of free hydrogen ions.
Correct.
One more big one.
It's getting hot.
Increased temperature. There you go. All of these factors, high CO2, high acid, and high heat, physically alter the shape of the hemoglobin molecule. They force that curve to shift to the right. And that is the Bohr effect.
So the very waste products of exercise are the chemical signal that tells hemoglobin, hey, we are working our tails off here, dump the oxygen, NOW.
Precisely. It's a brilliant localized feedback loop. The hemoglobin doesn't just randomly dump oxygen everywhere in your body. It doesn't dump it in your resting earlobe or your quiet pancreas. It specifically and aggressively dumps its oxygen cargo in the muscle that is hot, acidic, and full of CO2.
It raises the oxygen release from that standard 25% utilization to, nearly 100% when you combine it with the low oxygen pressure in the tissue.
It creates a delivery system that automatically targets demand. And of course, on the flip side, what happens in the lungs?
Well, in the lungs, it's cooler. There's less CO2 because you're breathing it out. So I guess the curve shifts left.
Exactly. A left shift means hemoglobin becomes more sticky. It has a higher affinity for oxygen,
which helps it grab onto the oxygen from the air.
It's the perfect cycle. Grab tight in the lungs, let go loose in the hardworking muscles.
The notes also mention one more factor in this section, something called BPG, 2,3-biphosphoglycerate. That's a mouthful.
BPG, yeah. It's a metabolic byproduct that's just kind of always present in your red blood cells. But what's interesting is that its levels can change. If you are exposed to chronic hypoxia, say, you move to a high-altitude city for a few weeks, your body starts producing more BPG.
And what does more BPG do?
It also shifts the curve to the right. It's the body's long-term adaptation strategy. It basically says, okay, we're living in thin air now, so let's permanently make our hemoglobin a little less sticky to make sure we can deliver enough oxygen to the tissues.
So the body adapts over minutes with the Bohr effect during exercise and over days and weeks with BPG for environmental changes.
It does. It's a multi-layered adaptable system.
Yeah.
But we have to talk about the villain, the molecule that hacks this beautiful system, carbon monoxide.
Section 5, the silent competitor. We all know CO is dangerous. We have detectors in our houses for it, but the source explains the mathematics of why it's so dangerous. And it's genuinely terrifying.
It really is. It all comes down to a matter of affinity. Chemical stickiness. Carbon monoxide, or CO, combines with hemoglobin at the exact same point that oxygen does. They're fighting for the exact same seat on the iron atom in the heme group.
A one-on-one competition.
The problem is, it's not a fair fight. CO binds to that spot with about 250 times the tenacity of oxygen.
250 times. So for every one spot CO takes, it's like it has 250 votes compared to oxygen's one vote. Oxygen doesn't stand a chance.
It's an absolute bully. Even a tiny, tiny amount of CO in the air will dominate the hemoglobin. The source gives a lethal math example. A partial pressure of CO of only 0.4 millimilli Hg in the air. Remember, oxygen in the air is around 160 millimilli Hg, and in the lungs it's 100. A partial pressure of just 0.4 allows the CO to compete equally with the 100 millimillimeters of oxygen for spots on the hemoglobin.
Wait, let me get this straight. 0.4 of CO has the same binding power as 100 of O2.
Because of that 250-fold affinity advantage, yes, it takes almost nothing. And the source says if the CO pressure in the air rises to just 0.6 millimilli Hg, it can be lethal.
That is such a minuscule amount of gas. It really highlights how fragile the system is to a specific chemical attack.
And the visual deception is what makes it a silent killer. Normally, when your blood oxygen is low, the hemoglobin changes color. It turns a darker purplish color, and your skin can look bluish. It's called cyanosis.
Right, you see it on the lips or fingertips. It's a classic sign of suffocation.
Doctors look for that blue skin. But cohemoglobin, the molecule that's formed when CO binds, is bright cherry red. Even brighter red than normal oxygenated blood.
So the victim, they look pink and healthy, rosy-cheeked even.
Exactly. Their blood is cherry red, but it's carrying effectively zero usable oxygen. The tissues are starving to death, but the color of the blood in the skin suggests everything is perfectly fine.
And because the patient looks fine, no one, maybe not even the patient themselves, realizes they are actively suffocating.
And there's another insidious layer to it. Remember how we said that about 3% of oxygen is just dissolved in the blood fluid, not attached to hemoglobin?
Yes.
The respiratory center in your brainstem uses the pressure of that dissolved oxygen to decide if you're suffocating and need to breathe harder. Since CO only attacks the hemoglobin, the dissolved oxygen level in the plasma can remain perfectly normal.
So the brain's fire alarm system doesn't even go off.
No alarm, no shortness of breath, no gasping for air. You just feel a little tired, maybe a headache. You think you had the flu. So you lie down for a nap, and you don't wake up. It is chemically stealthy.
That is chilling. The notes mention the treatment involves administering pure oxygen, which makes sense. You're trying to flush out the CO by overwhelming it with a competitor. But it also says they add 5% carbon dioxide. Why on earth would you give a suffocating person CO2?
It seems counterintuitive, but it goes back to that alarm system in the brain. The primary driver for your urge to breathe isn't a lack of oxygen. It's a buildup of CO2. So by giving the patient a little bit of CO2, you powerfully stimulate that respiratory center in the brain to make them breathe very heavily and very deeply. This creates a powerful washout effect to help clear the CO from the hemoglobin much, much faster than just pure oxygen alone would.
Wow, you're fighting fire with fire. You're using the body's waste product signal to save the patient's life.
In a sense, yes. A very clever clinical trick.
Okay, let's pivot from that dark topic to the return trip. We've dropped off the oxygen, or, failed to in the case of CO. Now we have to get the trash out. Section 6, transport of carbon dioxide.
Right. And CO2 is a very different beast from oxygen. The first and most important thing to note is its diffusion speed. Carbon dioxide diffuses through tissues about 20 times more rapidly than oxygen does.
20 times faster. Why?
It's just physically more soluble in the fluid of the cell membranes. It slips through much more easily. And because it moves so fast, the pressure differences needed to move it are tiny in comparison to oxygen.
So we don't need that huge 64 millimilli Hg kick to get it moving.
Not at all. Look at the CO2 numbers. The pressure inside the cell is about 46 millimilli Hg. The pressure in the arterial blood arriving is 40 millimilli Hg. The difference is barely 6 millimilli Hg.
That's a tiny little nudge.
It is a tiny gradient. Yet, because CO2 is so incredibly soluble, that tiny 6 millimilli Hg push is more than enough to move massive volumes of the gas out of the cells and into the blood. It flows like water down a gentle slope.
So it's extremely slippery stuff. It just wants to move.
It does, but transporting it in the bloodstream is actually more complex than transporting oxygen. It's not just about hemoglobin. The source says there are 3 main forms of transport.
Okay, breakdown time. What's form number 1?
The simplest is the dissolved state. Just simple CO2 gas dissolved in the plasma, but this only accounts for about 7% of the total transport. It's a minor player.
Small potatoes. What's next?
Form number 2 is carbaminohemoglobin. This accounts for about 20 to 25%. This is where CO2 reacts directly with the chemoamine radicals on the protein part of the hemoglobin molecule.
So it does hitchhike on the hemoglobin bus, just like oxygen.
It does, but it's very important to note that it does not sit in the oxygen seat. It doesn't bind to the iron. It binds to the protein chains, the globin part. It's a loose, easily reversible bond.
Okay, so roughly a quarter of the CO2 rides the hemoglobin bus in a different seat. That leaves the big one. Form number 3 must be the majority carrier.
It is, the bicarbonate ion. This is the heavy lifter, accounting for about 70% of all CO2 transport. And this involves a really cool bit of cellular machinery inside the red blood cell. This is where the red blood cell performs a kind of magic trick.
The notes here mention a specific enzyme, carbonic anhydrase.
Yes, this enzyme is absolutely packed inside the red blood cell, and its only job is to catalyze the reaction between CO2 and water.
What does that mean, catalyze?
It means it makes it happen incredibly fast. Without this enzyme, the reaction would be so slow it wouldn't matter for our purposes. With carbonic anhydrase, it speeds up the reaction 5,000-fold.
5,000 times faster.
It's practically instantaneous. The moment CO2 enters the red blood cell, this enzyme grabs it and a water molecule and fuses them together to form carbonic acid. This acid is unstable, so it immediately dissociates. It breaks apart into a hydrogen ion and a bicarbonate ion, which is HCO3.
So the red blood cell is effectively taking a gas, CO2, and turning it into a liquid-soluble salt, bicarbonate.
Exactly. It chemically disguises the CO2 as bicarbonate. This is how you can pack so much of it into the blood. But this creates a new problem. This bicarbonate builds up inside the cell. It needs to get out into the plasma to be transported.
Okay, so it just diffuses out.
It does. But bicarbonate is a negatively charged ion. If you just start throwing a bunch of negative charges out of the cell, you mess up the electrical balance of the cell.
You'd basically create a tiny battery.
Right, so the cell has a clever solution. To balance the books electrically, for every negative bicarbonate ion that leaves the cell, a different negative ion, a chloride ion, moves into the cell from the plasma.
It's a swap. One negative charge out, one negative charge in.
It's called the chloride shift. This beautiful little mechanism allows the blood to carry a massive amount of CO2, disguised as bicarbonate floating in the plasma, all without upsetting the electrical equilibrium of the red blood cells.
That is just an incredible level of complexity for something that happens billions and billions of times a second in your body. So now we have all the CO2 in the blood. We get to the lungs. We have to reverse all of this. We need to get it out of the blood and into the air.
We do. And this is where the final piece of the puzzle, the Haldane effect, comes in.
Okay, so we had the Bohr effect at the muscles. Now we have the Haldane effect at the lungs.
Think of the Haldane effect as the perfect mirror image, the flip side of the Bohr effect. The Bohr effect was about CO2 and acid making hemoglobin dump oxygen. The Haldane effect is about oxygen making hemoglobin dump CO2.
How does that work?
When oxygen rushes into the blood in the lungs and binds to hemoglobin, it physically changes the hemoglobin molecule again. This time, it makes the hemoglobin a stronger acid.
So it becomes acidic hemoglobin. Okay.
And this newly acidic hemoglobin does two things simultaneously. First, it has much less tendency to hold on to CO2 in that carbamino form, the hitchhiker form we talked about. So it just kicks the CO2 off. Get off the bus.
And the second thing,
The increased acidity means it releases a lot of free hydrogen ions. These hydrogen ions are now floating around inside the red blood cell, and they're looking for a partner.
and what's floating around in there?
The bicarbonate that came in from the plasma, well, that was converted from, the hydrogen ions bind with the bicarbonate. They bind with the bicarbonate. And when a hydrogen ion meets a bicarbonate ion, they recombine to form carbonic acid. The carbonic anhydrase enzyme then immediately reverses its action, splitting the carbonic acid back into water and gaseous CO2.
And that CO2 gas then flies out of the blood into the lungs and you breathe it out.
Gone. The source actually quantifies this. The Haldane effect approximately doubles the amount of CO2 that gets released in the lungs compared to what would happen from simple pressure diffusion alone. It is an active ejection mechanism triggered by the arrival of oxygen.
It's so remarkably coordinated. The arrival of the new cargo, the oxygen, automatically triggers the ejection of the old cargo, the CO2.
It's the perfect logistical loop. You don't have empty trucks driving around. The loading of one thing forces the unloading of the other.
Before we wrap up, there's a small section here on the respiratory exchange ratio, or R. This seems to be where our diet enters the chat.
Yes, exactly. R is a very simple ratio. It's the rate of carbon dioxide output divided by the rate of oxygen uptake. Basically, for every unit of fuel you burn, how much exhaust are you producing?
And that depends on what you ate for lunch.
It absolutely does. If you are burning pure carbohydrates, glucose, the chemistry works out perfectly. The ratio is 1.0. For every single molecule of oxygen you consume, you produce one single molecule of carbon dioxide.
It's 1 for 1. Very clean.
But if you're burning fats, the ratio drops to about 0.7. Fats are different chemically. They are more hydrogen dense, so they require more oxygen to burn relative to the amount of carbon they release as CO2.
So a person on a strict keto diet would literally have a different respiratory ratio than someone who just ate a big bowl of pasta.
Yes, distinctively so. For a person on a normal mixed diet, the average R is roughly 0.825. Scientists and trainers actually use this ratio in real time to measure what kind of fuel a person is metabolizing during an exercise test.
So if my R value is close to 1.0, I'm burning the carbs I just ate. If it starts dropping towards 0.7, I'm tapping into my fat stores.
That's exactly how it works. It's like analyzing the exhaust coming out of your car's tailpipe to figure out what kind of fuel is in the engine.
That is fascinating. We've covered a lot of ground today. I mean, we've gone from alveolar pressure gradients all the way to the chloride shift.
It's a dense chapter, for sure,
Yeah.
but hopefully it's a little less of a foreign language now.
Let's try summarize the big takeaways for everyone listening. If you're going to remember just 3 things from this entire deep dive, what should they be?
Okay, I think first has to be the safety buffers. Just remember that your blood oxygenates in only 1/3 of the time it has available in the lungs, and that your cells can function perfectly on a tiny fraction, just 1 to 3 milliliters of the oxygen they normally have.
Yeah.
We are built to survive extremes.
Right. Built-in redundancy. What's second?
The smart chemistry of hemoglobin. It's not a passive bucket that just carries stuff. It actively changes its shape and its affinity. The Bohr effect helps it know to dump oxygen in an exercising muscle. And the Haldane effect helps it know to dump CO2 in the lungs. It reacts to the needs of the tissue locally and instantly.
And third?
I'd say the danger of competition. Carbon monoxide is the perfect example. It shows us how fragile this whole system is if a molecule comes along that just happens to fit the lock better than the body's own key. It really highlights how precise and specialized the standard machinery really is.
I want to leave our listeners with a final thought, something you alluded to way back at the beginning. That concept of the limit of infinite blood flow.
Yes. For me, that's the philosophical nugget in all this.
We often think, if I could just get more blood to my brain or more blood to my muscles, I'd be superhuman. We think of it as a plumbing problem.
More flow must be better.
Right. But the source shows a hard mathematical limit. You can't pump your way past the laws of chemistry. There's a ceiling.
Right. And it invites us to think of the body not just as a mechanical pump, but as a chemical equilibrium machine. The flow is just the servant to the diffusion gradients and the chemical affinities. The chemistry is the real boss.
A chemical equilibrium machine. I like that. So take a deep breath, everyone listening. Feel that air rush in, and maybe appreciate the millions of tiny pressure gradients, chemical shifts, and atomic handoffs happening right now perfectly to keep you alive. Thanks for listening to The Deep Dive.
See you next time.